hazard that we face in the shop is cuts from sheet metal. So that's when it's laser cut or otherwise cut, there's almost always a burr that forms on the edge of the piece. And so if you run your hand along it, or your students are kind of playing with it, sometimes with pieces they like to try to, like, especially with thinner and larger pieces, you can make funny noise with them. But that's also a really good way to accidentally get it to slice open your palm. The first thing to know is that our first aid kit should always be in this bottom drawer, and then it just has a basic bandages, gauze. This is an eye wash kit, which that's another hazard that we face is when we're cutting sheet metal or other material that forms little chips, and those little chips can act as slivers, which most commonly will get in like hands, but like it's one of those good practices where you don't want to be touching your face a lot, because if you have like metal chips or stuff on your hands and you get in your eye, that can be bad, because they can be. A metal chip is more difficult to wash out because it will bite in at the sharp edge. Protective gloves, which we haven't had in the past. One, because it was a thing we had to buy. Two, I was a little leery of bringing them into the space because, yes, sheet metal cuts are the most common like injury that'll happen, but they're usually always pretty minor. Whereas when you wear a glove, and if you're working with a power tool while you're wearing a glove, it is very easy for something to happen where your glove gets caught in the rotating power tool, and then that ensnares and entangles you and sucks it in further and causes way more damage than would have happened if you just had bare skin.
So don't wear gloves if you're using certain...
If they're using really any sort of power equipment that moves, they shouldn't use gloves, and that's a pretty big one. We have all of our power tools over here. They're fairly benign in terms of how bad of anything have happened, but if they're used carelessly, like it can always happen. One of the ones to watch that I have caught a few times, just people using a little haphazardly, is a little sawzall, because with this there's a lot of vibration moving back and forth quickly, and it's easy for it to slip. So when students are using power tools in general, but especially this one, they should always like have the workpiece like clamped in a vise to help stabilize it. This one would actually be a little probably smaller vise. We have our own bolted to the table, which would be ideal. And like this is a great example here. Here we have this. Ideally, like we wouldn't leave our power tools laying out with the battery still in them and a blade. Just because it helps keep things cleaner and it's less likely for someone to pick up absentmindedly and play with. But yeah, when they're securing the workpiece, make sure it's clamped securely. Like you can actually put a decent amount of force into the workpiece to secure it. We should have, I don't know where they went, they used to be right here, but some magnetic nylon jaws for the vise that I had Aaron purchase a couple months ago. And the purpose of those is so that way you can open up the vise wider and put those nylon jaws on the vise. So that way, if you do need to clamp a workpiece tightly and not have the steel teeth dig into it and rough up the surface finish, the nylon is very useful for that. And it's also useful if you're doing rounds. There's grooves in those nylon jaws. So that way, if you have a round piece of material that would be more likely to slip, you can put it inside of the round groove and tighten down on it. Oh, here they are. So they have all sorts of different sized and angle with predefined geometry. So it makes it easier to get a good hold on whatever workpiece you're working on. A lot of safety comes down to fundamentals of using good work holding and having good setups. So that way you're not like trying to cut something at a weird angle, which sometimes happens with something when it's on the robot, and that's the only way to get to it. But the better, like, students can set things up, the better quality will come out of it, and there'll be less likely to be some sort of accident. Another thing I've seen to watch out for on these hand tools with these sawzalls is making sure students seat the blades all the way. These blades have they have a tang and then a hole, and there's a pin that as you rotate the front piece, retracts inside, and so it lets you put in, and then you can rotate it until you feel it click into place, and then put the battery out of the tool, and you can give and make sure, obviously keeping your fingers away from the teeth, make sure the blade is seated, so that way when they go to turn it on, the blade doesn't come under, that way it's not partially attached, so that way it doesn't come under load and spring load and then come loose and fly off somewhere.
And they put the checker without the battery.
Oh yeah, it's just like that way you can't hit your trigger as you're handling out by the cutting edge.
Probably nice to change the blade off battery too.
Yeah, yep, yeah. It's something that I can be more mindful, pretty much everyone can be more mindful of, because it's always easy just to like, and if you have experience or don't have experience, it's easy to just, in my case, say I know what I'm doing and I absent-mindedly like pick up the tool, change it out with battery still in it. And there also is a safety on these that locks out the trigger so it can't actuate. Then the next, probably one of the more likely things that I see potential for students to injure themselves on is our belt sander. Because this moves the abrasive belt fairly quickly, and if this is actually worn to the point where it probably has to be replaced. Because yeah, I should actually probably take this belt off. This is a good thing. So here, if everyone wants to see a little closer, you can see there is the red material on the belt, and this red material is the abrasive, but you can see especially here, it's getting worn to the point where you can see a blue backer underneath. That is an indicator that we need to take this belt off and replace it with a new one.
Is that like a wear? You know how like cars have the indicator type thing?
Yeah, it helps you identify the contrast with the red and the blue, so that way you're not trying to look at red and brown.
Okay.
Probably get better replacement than pad too.
Yeah, no, there hasn't been a pad on here in a long time.
Oh, there's on again? Okay.
Unless someone put one on, I haven't seen a pad on this in years.
Oh, okay.
I've seen people try to use it.
That's actually the safest part thing to use on it.
Yes.
You can hold them.
Because you have a table supporting your work, it all goes back to setups.
Yeah. And we should replace that.
But yeah, in this case, to change out the belt, there's this cam action lever, and then that loosens the belt up, and it should just slide off in my direction. Other thing to know with this is when students are using it, it is important that however, say they have a piece like this that they need to sand down and get rid of all of the burrs on the edges. For a piece this small, I would want to see a student or anyone using it grab a vice grips. This is a sheet metal pliers, which this is really useful for bending thin gauge sheet metal. So this will support whatever you're gripping with it. then whenever you're gripping something, I always like to use the fine adjust, and essentially I like to get it so it's sitting tight with the fine adjust, and then I open it up and give it another quarter to half turn, and then that gives you a lot more gripping strength without like crushing the material or putting in excessive force. And so now, if I want to sand down this edge, I can do this in a nice supported manner, where my fingers are further away from the abrasive surface, and the workpiece is less likely to go flying if it comes loose from my hand.
And the belt comes towards us, right? It spins towards us?
It goes back this way.
Okay.
So that's this backstop. If you're doing a larger piece, this backstop can be very useful. So if you see a student trying to do this, you should stop them and correct them, because it's just going to chatter and vibrate and be hard to hold. So they need to get it flush up against the backstop, because then there's not going to be vibration and flexing. At the same time as they do that, it's important, if you see a student doing something like this, you also want to stop them if they're like right up at the backstop, because you don't want to get the piece wedged in here at speed and force and then have it like push a hand down. Sometimes like you do want to bevel an edge, so if you do that, if I'm beveling an edge, I want to put it at like an offset angle further out on the front, so there's plenty of clearance to a pinch point there.
This would be a good example where not to wear gloves, because the glove would get you really hung up in there, I would imagine.
Yeah, it could.
If it went in and got underneath.
The good thing about most of our tools is they're small enough where like they probably won't break arms or like cause catastrophic injury, but they can definitely still cause like a trip to the ER. For tools that can actually cause like significant bodily harm or death, the mill is the one that like to watch out for in terms of students using that carefully. Our mill still isn't all that powerful; it's only 1.5 horsepower. But if someone like royally, like say if they had their hair down, that would be the biggest issue with the mill, because that would have enough power to scalp someone. So loose hair is another big one. So just any rotating, moving thing, loose hair, watches, wedding rings, preventers, and then safety glasses. That's one thing we always have to remind students of. Another one, we recently, with the gloves that we got donated, we got the disposable hearing protection, the scrunchy earplugs. So we have this disposable sets of those. If students or mentors, say we have a lot of tube stock that we need to saw, like the saw does make a fairly significant amount of noise, so if someone's going to be sitting there sawing for half an hour, they may want to grab those.
One thing you might show on here that I really realize is there's an alignment adjustment to keep the belt
Tracked, yes.
trapped. Yeah.
Yep, which
Could cause some safety things if they don't get it, right?
correct. If
Going
this,
off.
yeah, when the belt gets changed out, ideally it's done by someone who knows how to change the belt and make sure it's tracked. There's this knob here that as turning this, it moves. There's a bevel gear, and it moves this roller in and out. So that way, if you install a belt and it wants to wander one way or the other, you can adjust with your fine adjust in here. In theory, once it's set, it probably shouldn't move that much when you switch out belts, but belts have their own variation from manufacturer. So
And students fiddle with things.
that's true. This is a really simple tool. It's generally safe, but it is a crush and pinch hazard. Because when you're pulling on this, you can put out a little over 1 ton in terms of pressing force. So if a student's like doing something absent-mindedly and they get a finger in there, they could break a finger. We use this to like install or remove bearings is what we mostly use it for. And it works really well for doing that. When students are trying, this isn't so much as a safety, but protecting our bearings. making sure they're using a press tool that aligns to the correct size of the item they're trying to install. So that way, to be conscientious of, there is roughly 1 ton of pushing force. So if you're pushing on a bearing and you're pushing on the wrong part of the bearing, you can damage the bearing. But probably the other thing, if they're pushing on if they have a precarious setup where something's jammed in here, like not aligned, it's possible as you're pushing, it could shoot out and go flying and become a projectile. Likelihood of that isn't super high, but it's just one of those, seems like common sense, but keeping everything aligned and concentric. Our next tool that we've used occasionally, there's definitely a few times a season it comes up, is the little benchtop lathe here. This is like a 3/4 of horsepower and only runs in high gear. A student shouldn't use this without probably myself or Chad, or any other mentor that wants to use the lathe. I'll happily teach them the basics on it. But this is just the biggest hazard with this is entanglement into the machine. So getting hair caught in the spindle. When the machine turns on, this is the e-stop on the lathe. So to turn it on, I don't know if it's plugged in. So to turn on the lathe, you lift this up, and then there's a red off button, which when you press down the e-stop, all it does is push this same button, and the green power button. It turns on and lights up the RPM readout. And then there is this forward reverse switch, and then there's spindle speed control. With the lathe, one thing to be, in terms of hazards of where to watch if a student's using it, and to be, the chuck spins and a workpiece is clamped on the chuck, and the tool stays stationary, and you move the tool using the carriage. This lathe does have a power feed on the carriage, so right now power feed is not engaged, but for pinch points we have the, or in points of entanglement, we have the chuck itself, and on this half we have this gear train. Normally this gear train does not rotate or move, but it can be engaged, and when it does engage, the lead screw turns on, so that is another point of entanglement potentially. And if you engage the lever, it engages a half nut and runs the chuck in at a set speed.
Is there a way to disable the use of that feature?
Of what?
Because that all the gearing is just to run the feed, right?
Yes.
And I don't see any students ever needing to do that.
It's nice if you're turning an OD.
I know. Oh yeah. Instead of manually turning it.
Yep. Because right now the gearing in here will not get you a thread.
Okay. Oh.
So yeah, if you wanted to thread something, you swap out the gears.
Okay.
Yeah, right now I think it's like a couple thousandths per revolution in terms of advance. And then X-carve. The X-carve is the spindle gets tools moving really quickly. So they're moving at anywhere from 15,000 to 35,000 RPM. So if something breaks on the X-carve, it's going to break quickly, which is why there's polycarbonate in front of it on one side. If we ever get some larger sheets of polycarbonate, I would add another one to that side. That side, the way it's positioned here, there's not a lot of traffic there, but it'd still be nice to have another sheet. Safety-wise, yeah, the biggest thing is if a tool breaks and it's moving at 35,000 RPM, there's a good chance that it's going to go flying somewhere. Most of the time when a tool breaks, so there's nothing too dramatic that happens, but occasionally if it breaks in the right manner and the geometry gets snagged on something, then it can bounce off with a lot of energy. But the machine's completely enclosed on these two sides. The big thing on the X-carve is if it needs to stop, there's the e-stop. and this is the same style as the mill, where it's a rotate to disengage the e-stop, and if anything goes wrong, you just need to press it on it. And then power to the control electronics isn't what you would use in the case of an e-stop, but it also would shut down the machine. Any questions about that so far? Alright, the mill we'll skip for now, so we'll come back to that. For organization, this is one of the projects we're working to get all these tools better organized so we can find what we need when we need it. But a lot of, it's not all I thought it was, but there's a drawer, like one thing to watch for here. We do have, these hacksaw blades are contained, but like they are, and this will be addressed when we do our storage and organization, like just loose saw blades sitting in this drawer. So having students be conscious of like what they're grabbing and just common sense there. Another good thing is it's not a huge issue with twist drills, but if someone's handling a twist drill, if they're grabbing it like here, we have cheap twist drills, so generally these flutes aren't super sharp. But if you grab a twist drill or an end mill in the wrong way, they can and will cut you. That's especially true with all of the X-carve tooling because that's sharper than the rest because it's not designed to cut through steel. Oh, that's a good point. On the X-carve, I came in last Saturday. I've said forever that the X-carve can't cut aluminum, but I've never tried to prove it because I kind of knew in my gut it wouldn't work. So I came in Saturday to like try and prove the fact that we can't really cut aluminum effectively on the X-carve.
Somebody's gnawing on it.
Mm-hmm. Yeah, there's just too much chatter. It's not a rigid enough machine. So the X-carve should only be cutting wood or plastic. The mill is capable of cutting pretty much any material we can throw at it. The CNC mill here, hope that we can have up and running to utilize a little bit this season. All the same safety things we learned with the manual mill apply to this, and then with the added kind of overlap with you have to know a little bit in terms of the programming, which isn't all that difficult to be able to successfully use it. So to safely use like the CNC mill, they need, at this point, they pretty much have to work with me until I can get more people trained up on it. And moving on. We do have, this isn't a huge safety thing, but like we did get some new clamps, and these are nice forged bar clamps that can put out a lot of force. So if students, I absolutely encourage the students to use it, but then if they're clamping something down, to consider the amount of, like, how much force are they twisting this with, and if they're putting together, say, aluminum structure, that the structure doesn't, say, slip under the clamping load, and then aluminum bar gets kind of cantilevered and thrown with some force. Like, that's a scenario that could happen if the clamping is set up and things aren't all quite aligned. It's back to a lot of safety comes from following, like putting things together in a clean and aligned way instead of just kind of sloppy work is less safe work. Then we have the box and handbrake. This is all human powered, but the biggest hazard to it is pinch points. So when we want to bend a piece of sheet metal, there's the upper portion, which this clamps by, you want to have, if you see a student using these, generally these two handles should move in tandem. Yeah. So that way, if you're moving, if this side's down and this side's up, now you kind of, what's the right word? It's not a, you put a torsion or a twisting force. Yeah, like you're trying to bend the piece, the top jaw like this, which is not designed to. So as you move these, like you want to keep them moving roughly in tandem. And then these are cam operated and they're adjustable. They are set to the right position currently, I believe. So that we shouldn't, because we have a standard sheet metal size for these, we shouldn't really need to adjust them. But they have a lot of leverage and then a cam on top of that lever. So when you pull these down, if a finger or something is in there, you're going to be applying tons of pressure to it, so it would break the finger. And then to bend, these are painted yellow for a reason, because as you bend it, these swing back. So if someone is standing, say, here and it bends back, these are going to come up, or likewise if someone is back over here standing and I go to bend a piece of sheet metal, they're going to come down. And they actually do have, they're not plastic, they're solid pot metal. So they have quite a bit of weight to them, and that's so that way when you lift this, you don't have to apply a giant amount of force to lift all the heavy weight of this cast iron down here. And then as the student uses it, they can use an angle cube to measure the angle that they're bending to. But that gets into less of safety and more of how to get a good part. And so then that's how we make our sheet metal parts. Oh, this is a great one. This actually, this is something I would like for us to get done before build starts, but we need to probably change the oil in this air compressor and make sure there's no water that's accumulated in the tank, because I don't know if I ever have checked for that. Because when an air compressor is pulling in air, it's pulling it from the atmosphere, and the atmosphere has water in it. And so as that air is getting compressed, some of that water gets trapped and builds up in the bottom of the tank, and it can, over time, cause rusting to happen on the bottom of the tank. And as the metal rusts, obviously this is a pressure vessel. So if you look on YouTube, you can find like people who have had air compressors in their shop for 15 or 20 years, and they haven't done any maintenance on them. And there's videos of like them filming some other YouTube video and their air compressor explodes and blows up the garage nearly. This one isn't quite that large, but I would not want to be anywhere, I wouldn't want to be in the same room if it did explode. So yeah, and that's just common sense too. Like students like obviously should be treating it like a pressure vessel, which they don't necessarily understand the context of. So I think communicating and understanding, like, don't like be doing reckless things with it. We also need to replace, it's not necessarily, it actually kind of is. I didn't realize that was duct taped. We need to replace this hose.
And what do we want for policy about cleaning with air? Any factory I've ever worked at, you don't clean with air because with eye projectiles.
Yeah, no, I mean,
because that's what they're doing there. They're cleaning something. With that nozzle on there, that's all they could be doing with it.
Yeah. I would say, like, they should not, first rule is, like, don't blow yourself down with it, because if there's oil at the tip of this, or, especially, not that this would be soaked in oil, and it's not that we have a ton of oil around here, but oil with air under pressure can cause hydraulic injection, which is essentially just means the air accelerates the oil droplets fast enough that they go through your skin and underneath it, and to deal with that, like they need to, like medically, they essentially like rip open the affected area to take out all of the flesh that might have been exposed to oil. So yeah, people shouldn't dust themselves down with it. You shouldn't have them blow chips saw down either. If they need to get rid of chips, they should use a shop vac because that'll suck them up and not just spill them back onto the floor somewhere. Oh, the other thing to know is, and this goes for really any compressor, same with our compressor on the robot, or this one is, there's a regulator on the compressor, and that sets what the maximum pressure is. There's an electronic switch that should turn off when the pressure exceeds the like hits the charging threshold to what the tank is nominally rated to hold. And then there is an emergency blow-off valve. I haven't ever seen an issue, but if for some reason anyone ever puts tape on this or tries to zip tie it or something, like that is an absolute no, because that means if the switch fails and it keeps going over pressure, the blow-off valve has now been sealed shut, and now you have a bomb.
Thank you, MacGyver.
The drill press, a lot of the rules that we'll go over with the mill apply with the drill press. The drill press should only be used as a drill press. So like, there shouldn't ever be an end mill in here. An end mill is a type of cutter that we'll cover in the PowerPoint quick. And with our drill press, they should be clamping whatever workpiece they're drilling holes into to the table itself and lining up where the hole needs to go. Or using this drill press vise and putting the workpiece in there. The main hazards with the drill press are very similar to mill, where the threat of entanglement in the rotating spindle, or the drill press potentially throwing the workpiece, or another one is if you have a piece of sheet metal like this, if this piece was like a little smaller like this, and I was just trying to do this by hand and it came loose, there's a good chance that the hole I'm drilling, the drill bit's gonna catch in it, and now all of a sudden this piece of sheet metal is gonna spin around like a blade and come around and whack my hand and potentially leave a good cut. So you always want to have clamps or a vise securing the workpiece, so that way students aren't trying to hand hold a piece. And even if it's eventually like a piece like this, like say you needed to put a hole in the end, there's no chance that this could spin around because I have a lot of leverage, but I'd still say the student should use a clamp, because now I don't have to deal with this wobbling, and here's the word rigidly, and rigidity is like the key fundamental to getting good machine parts.
You had that on the other side though.
Yeah, if I had this on the other side and it came loose. Yep. So that gets back to, yeah, thinking about your setups. If the piece is set up here and somehow does spin, then it's going to hit cast iron column instead of coming around, like Chad pointed out.
There's also a risk that the drill blade will snap and go flying too, right?
Yep, that's not super common, but
I break them all the time.
The drill press does help you compared to using a hand drill.
Yeah.
You will break way less tools using a drill press than a hand drill.
That makes sense.
So if you see students that are using hand drills to do things that could be done on the drill press, you should move them towards the drill press, because they'll get a better result faster, and there isn't really a appreciable difference in safety between a hand drill and a drill press, especially at this size. Then here, we have our cutoff saw. Cutoff saw, there is this piece clamped in it, and this piece is getting to the point where it's questionable to cut this piece in a cutoff saw. the cutoff saw is really, really good at cutting profiles. So rectangular tubing, square tubing, quarter inch, like that you can cut all day because there's enough material there that's stiff enough to hold itself as it's being cut. But as you get into like a thinner sheet metal, like you can bend just physically with your hand, and the machine is putting more force onto it when it's being cut than you can by hand. So I would say you probably don't want to use, in this case, this is about a 1 inch wide piece of aluminum. I would say you don't want this to cut a piece of this size on a cut-off saw. The other thing is, do we have any angle iron?
I get that one.
Perfect. So the cut-off saw, when things are being clamped for cutting, orientation does matter. If I was cutting this piece of 1/4 inch aluminum, and imagine it was a little longer, because this is starting to get to the point where it's too short to be safely cut, because my vise, this swivels to apply an even pressure, but if I am pinching this part like this, and I am off center where the material isn't actually being directly pushed on by the screw, that is going to leave this, even if I try to tighten it down, it might seem tight enough as I like move it with, as I give it a tug, but as the saw digs into it and starts to cut, cutting force could exceed, and then you could have this break loose and go flying. So the piece being cut always needs to be extending, ideally the full width of this swivel. And then orientation. If I was cutting this piece, I would not want to cut it. I could probably, like safety-wise, I could cut it in this direction, but in terms of machine life, or the blade life, and the speed of the cut, if I'm cutting, I want to minimize the cross-sectional area that I'm cutting through. So if I have the piece laying down like this, the blade has to scrape away all that material, versus if I put it upright, that's a lot less cross-sectional area for the blade to get through, so it'll go faster and be cleaner that way, which gets into angle. A lot of students' inclination is to clamp angle like this, or like this. The best way to clamp angle is always by making an A-frame with it.
It won't hold it that way.
What?
It won't hold it the other way. It'll fly out.
Yep.
You want to just show that how it rotate?
Yeah. So in
Center that way.
because as the saw is pushing this way, it's pushing down and back. But even though it's pushing down, I won't tighten this by hand because I physically might not be strong enough to make it come loose, but the machine absolutely would be. But it's going to do that. And then once it does that, it's rotated up, and now there's less cross-sectional area this way, and now there's a loose piece that's being engaged by the saw blade.
So I actually watched one of the FTC students last week. He had a U-shape perforated thin material that he was cutting in here. He didn't go through it slowly. He just jammed into it, and a chunk went flying off the window and into the thing there very hard.
Yeah.
So,
yeah, I would say,
and
unless FTC has had this, unless really anyone has been shown how to use the saw, it's something we have. It's not hard to use, but you should have to go through some basic know-how before you do use it.
Yep.
So.
I'm sorry I interrupted you before you clamped it correctly.
Oh, yeah, so clamping correctly is making an A-frame or triangle shape with it by laying it this way. And what that does is, because this is sloped now, as this is pushing in, and it's clamped, it really doesn't have anywhere to go.
How about a U shape? Would the two loose ends be pointed down?
So yeah, like a C channel.
Yeah.
Do we have any laying?
I don't see any.
But yeah, more or less a tube, but with one of the walls missing.
Right.
Yep.
Would you do it face down then, or the two light?
You want to minimize cross-sectional area. So in this case, like a tube like this, if this wall here was missing and it was just these three sides,
Yep.
I would want to put it vertical like that. But the caveat to that is like this, if it is a thin gauge sheet metal, we don't want to be cutting it on this saw. This saw should really only be cutting 1/8 inch or thicker material, and that's even a little pushing it. A tube like this is probably a 63 thousandths wall, but this tube's fine to cut on a saw because it's a tube that is supported by itself on all sides, where versus a open sheet metal profile, whether it be a U or an S, there isn't a self-supporting structure there. So unless it's like 1/8 to 3/16 of an inch, I wouldn't cut it on this saw.
So really, he had no business with it because it was thinner than that.
Yeah, absolutely. Yeah, absolutely.
No business using it.
Yeah,
Okay.
that's asking for the piece to go flying across the room.
Yep.
Really, we need to get the bandsaw set up.
Back up and running, because
Yep.
the bandsaw is the saw to use for thin sheet metal, or regular thickness stuff too. But this saw will make much quicker work with thicker material, and it makes a square. This saw makes a very square and accurate and clean cut. This bandsaw, even when it was new, never made a square cut. Bandsaw is very similar in terms of all of the clamping theory that we talked about with that saw applies to the bandsaw. One thing that this app won't open up all the way it's sitting on the table right now, but one thing that I wouldn't want to see students doing until we eventually get a more permanent fixture designed is because there sometimes is utility to make a cut. If this is pinned vertically, then you turn this from a horizontal bandsaw that's good at cutting shapes into a vertical bandsaw, which can be much more useful for cutting shapes out of sheet metal blanks. So if I had a shape that I needed to cut out of this piece here, I couldn't cut it out at all really with the bandsaw in its horizontal configuration. But that's one thing I would like to get is this, so we can pin it in a vertical position, so we can use it to cut out and make a little table for it that mounts on, so that way we can convert it over for either or. But currently we can't do that. So
So don't wear gloves if you're using certain.
if they're using really any sort of power equipment that moves, they shouldn't use gloves. And that's a pretty big one.